Welcome students on today's lecture on design of compression members. In the previous lecture we have solved a numerical wherein we have designed an angle strut using a single angle section. So today we shall see how the design has to be done for double angle strut. So let us take a numerical. Design a angle strut using a double angle to carry a load of 400 kilonewton. Use welded connection, take length of the member as 2 meter. Now the given load is 400 kilonewton, so I will assume it to be a working load. Hence we have to find out the ultimate load or a factored load, which is working out to be 400 into 1.5, 600 kilonewton. Now as we have a formula for the compressive stress, PD is equal to A into FCD. Again we have two unknowns, area as well as the compressive stress. So let us assume the FCD value. You can see PD is equal to A into FCD, both are unknown. So I will assume FCD. So assuming FCD to be as 120 Newton per mm square. So area required, we get load divided by the FCD, which is working out to be 50 centimeter square. Remember, whatever area we are getting, this is whole together for a double angle section. Now we need to choose a section, double angle section, from the steel table. Now in the previous lectures we already concluded that when the connection was on same side and on the either of the side, okay, so the strength is more for such kind of connection. So generally we will find out the angle section, choose a section of such kind where the longer leg is connected. Now let us try an angle of 200 by 100 by 10 as 200 by 100 by 10. As you can see from the steel table, the sectional area is working out to 58.06 and our required area is 50, and the RXX and RYY value we shall note. So RXX for this you can see is working out to be 6.46 and RYY is here. So there is a gap distance, so back to back angle. So let us take 10 mm gusset plate. So 10 mm means 1 centimeter. So for this it is working out to be 3.68. So I have noted down here 6.46 centimeter and 3.68. Least is, so this component least, so R minimum is 36.8 mm. So let us find the ratio. Now assuming L is equal to 0.7 L because it is a welded connection, then lambda is equal to LE by R minimum. LE we have found out, that is 2 meters, that is LE 2 meters into 0.7, and R minimum is this. So we are working out lambda is equal to 38.04. Now here there are more than two sections. So if you happen to see the table number 10, the classification works out to be as the buckling class C, as it is a built up section. You can see for built up member it is classification C, and lambda value is 38.04. So let us refer the table number 9C and find out what is the value of FCD for 38.04. So for 30 it is 211 and 40 it is 198. So working out for the 38.04, so the FCD is working out to 200.55 Newton per mm square. The compressive strength is nothing but PD into AE into FCD. So AE is nothing but the area which we have provided into the FCD value. So it is working to 1164.3 kilonewton, which is greater than this, hence it is safe. Now we need to provide a connection for it. They have said for welded connection. So assuming that we are providing two sides weld. So first for a welded connection, so this is how the EXX and CXX value have been taken, that is CG value from the steel table for the angle section. Now size of the weld, as it is a round one, so 3/4 of angle thickness. So 3/4 of angle thickness is working out to be 7.5. Let us take 7 mm. So the force is equated to strength of the weld. Force is nothing but whatever the load. This is for single angle. So on the other side you can see there are two angles provided. So we are calculating it for a single section. So this load gets divided 300 here and 300 here. Let us design for single section. So for single section the load is working out to be 300 into 10 raised to 3, and this is nothing but 0.7 of S into L into Fe divided by root 3 gamma m w. So, substituting we get the total length of the weld as 323.30 mm. Now, we have to find out L1 and L2 because we are providing here and here. So, let us take, so you can see here the connection. So, let us take the movement about the section. Taking movement about this section, so after computing, that is equating the equations, so we can get L1 as 112.51 mm. Hence, we have found out L1. If we deduct L1 from this, we will get the value of L2. So, L2 is working out to be 210. So, providing L1 as 115 mm and L2 as 215 mm. So, provided here. So, this completes the numerical for the double angle section. In the next lecture, we will see how to design the columns. Till now, we have learnt about how to design a section using a angle sections for a compressive stress, that is single angle and double angle. Thank you. Thank you students. Please practice. Stay home. Be safe.